All right, so now we're going to be looking at resistors. Let's look at just a wire, as that's a great resistor. You can notice how some of these wires are a little solid piece. Some have a lot of little strands to allow for lots of freeways to go through. Usually, and lots of lanes on the freeway. Makes it so you can get more current flow. Look at this one here. So you can see how when they bundle them up, they can get a lot more flow through them. They offer less resistance. And you can also notice how thick this extension cord is compared to this one. This one's pretty thin. So what about how much resistance it has, and does it depend on thickness? You bet. Here's some very, very small resistor circuits. As you can see how important they are to electronics is understanding what you're doing right here. So depending on the material will actually affect the resistance. So it depends on kind of the chemical properties of it and how easy it is for those electrons to move from one location to another. And we have copper, which has a very, I'm going to zoom, oops, maybe I'm not going to zoom in on that. There we go. So let's zoom in on the resistance. This is like the resistivity. So how, let's see, you want a really low number. So copper's pretty low. And what has a high resistance? Air, extremely high, with 10 to the 16th power. We can look at wet wood, has quite a bit of resistance, but you could still probably go through it. And let's see if they show you the difference between the water. No. So drinking water, let's see, that would be 0.2. What are the units on this? Well, let's look. And oops, it says ohm meters. Ohm meters. What do they mean by that? There we go. Sorry for making you dizzy. So let's take a look at resistance. Resistance is proportional to the resistivity. So this, all that we were looking at over here, is all of the resistivity. If this value is high, then it has a lot of resistance. So you wouldn't want to use it for a wire. That's why copper has a low resistivity. The longer it is, the more resistance. So the longer, the more resistance. That makes sense because it'd have to travel a long ways. How about area? They're talking about the area, like the cross-sectional area here of the wire. Oh, well, the bigger the wire, the easier it is to flow through. That's why it's in the denominator. That's an inverse relationship. So the area, or how big in diameter the wire, that goes the other way. So it's really big, it's going to have a low resistivity. Now, let's just throw a number in here. So let's say resistance is equal to some number divided by 3. Let's say the cross-sectional area was 3, and that area is meters squared from geometry. And then another one, let's say we have some number and we divide it by 9 meters squared. You can see when you're dividing something by 9, it's going to be a small value, whereas dividing something by 3, it's going to be a large value. So the more area you have, the smaller the resistance is going to be. So go ahead and put this equation in your notes. And I would also draw this cool picture. So the longer you have for your wire, the more resistance. But the bigger the wire, the less resistance because it goes through much easier. Now, look at an electric toaster. That actually uses a really long wire to get a high resistance. And then it heats up. Some natural circuits that you might have seen. Nerves in your body, it's actually a natural circuit. So your nerves are your wires. Electric eel's tail is a natural circuit, and so is lightning.